The new unit that we're starting today is called circular motion and gravitation. And we're going to focus for the first while on the circular motion part of that unit. We're going to define a term, first of all, uniform circular motion. Uniform means kind of infers that something isn't changing. Something isn't changing. Uniform circular motion means that we have an object going in a circle, right? Circular motion, something's going in a circle, but the speed of the object isn't changing. For instance, I'm going to take my keys here on the end of the lanyard here and swing them around. Okay, that's circular motion, right? If I change the speed of my keys, speed them up, slow them down, that's still circular motion, but it's not uniform circular motion. Okay, when I have them going around in a circle like this at the same speed the whole time, that's uniform circular motion. And that's what we're going to be talking about in this unit is uniform circular motion. Circular motion in which the object is moving at a constant speed. Now we're going to define two terms and then go back to another term that we clearly know what means already, speed, in order to kind of get us into this analysis of uniform circular motion. The first term is called frequency. Where have we heard that term before? Where have we seen that term before? Where have we used that term before? Not necessarily in the context of physics 20, but just somewhere in life. Where have we seen the word frequency? If we're talking about the frequency of this, we're talking about what? Give me an example. Give me an example of where you've seen that before. I'm just going to pick names here today. Give me an example of where you've seen frequency before. Olivia. Oh, sure you do. Sure you do. The frequency of an event. The frequency at which this happens. What's the frequency of Physics 20 class? How frequently does Physics 20 class happen? Once per day? Okay. Once per day? Okay. So physics is happening once per day, or you could say 5 times per week. What's the frequency then? What's another situation in which we've seen the word frequency before, or the term frequency before? Sonia? Okay, good. What's the frequency of your birthday occurring? That's a perfect example, actually. What's the frequency of your birthday? Good, once per year. Or if your birthday happens to be on February 29th, once per 4 years. You still really have a birthday, right? It just doesn't have a day for it. Frequency of class is once per day, or we could say 5 times per week. The frequency of your birthday is once per year. What does frequency mean? If those are two good examples of frequency. What does frequency mean? Let's say, Tori, what does frequency mean if those are two examples of frequency? Good. How often something happens. Now, we're going to define it in a slightly more physics-like way, but in the end, that's what it boils down to, is how often something happens. We're going to say it's the number of cycles. Okay. One birthday to the next is one cycle. One physics class to the next is one cycle. So we're going to say frequency is the number of cycles per unit time. And what do we mean by that? Well, we could say per day, one physics class per day, or the unit time could be a week. 5 physics classes per week. Or we could say the unit time is a year, okay? 1 birthday per year. So we've got the number of cycles, the number of birthdays per unit time per year, the number of physics classes per day, the number of physics classes per week. How often something happens? It's the number of times something happens per amount of time. Now, the symbol for frequency is going to be a lowercase f. Don't get that mixed up with force. Force is a capital F, and force and frequency mean two completely different things. I want you to always, especially now, write force as a capital F and write frequency as a lowercase f. You start calling force a lowercase f, you're going to start sometime mixing it up with frequency. It's not the same thing. Frequency is lowercase f, and we can find frequency by deriving a little equation based on the definition. If it's defined as the number of cycles per unit time, then we're going to say we can calculate it by dividing the number of cycles over the time. Now, what units do you think we'd use for frequency? Let's look at the equation that we just derived from our definition. What units do you think would apply here? Well, the number of cycles is just a number. I could ask you, Miles, how many fingers do you have on one hand? 4, or depends on whether you count your thumb as a finger. I was going to say 5. But if you don't count your thumb as a finger, no, we'll go with that. Okay, 4. The number wasn't the important thing there. What he said or what he didn't say after that was the important thing. Okay, I said, how many fingers do you have on one hand? Miles says 4. He didn't say 4 meters or 4 kilograms or 4 anything units, right? He just said 4. A number is just a unitless quantity. We don't have a unit that's associated with that. How many fingers do you have on your hand? Whether you're saying 4 or 5 or 7 fingers on one hand, we're not going to associate that with a unit. It's just a number. So the units that are associated with the number of cycles is nothing. Okay, we could just say it's cycles, right? The standard unit that we have for time would be probably going to be the second. So it would be cycles per second. The number of times something happens per second. Now, we could also say per year or per day or per week, but the standard unit is per second. Just like for speed, we can use kilometers per hour and miles per hour, but the standard unit is meters per second. Now, we can write the frequency in cycles per second, but there's one abbreviation that we can use for cycles per second, just to shorten it up a little bit. So we don't have to write cycles per second, such a long quantity or such a long unit out every single time. Does anybody think they might know what that other one is? One person's got it. I'll tell you what, it hurts me right now. It hurts me right now that nobody else is coming up with the answer for this question, okay? It really, really hurts me that nobody else can think of what unit is the same thing as a cycle per second. Hurts me a lot, actually. What is it? It's the hertz, right? Not H-U-R-T-S, but H-E-R-T-Z. We're going to abbreviate it as H-Z. So frequency is the number of times something happens per unit time, but usually per second. And the units are going to be hertz. H-E-R-T-Z. Where have you seen that one before? Probably on your radio. I mean, most radios now are digital, right? Okay, but sometimes after the little, right beside the number, okay, I listen to the Fan 960 lots. So I like listening to sports on the radio. Depends on your radio. It might say 960H, KHZ, kilohertz. Or if you're listening to, I don't know what station you guys listen to. I used to listen to CJ92 on the radio, sometimes on FM. It might say 92.1 MHZ, megahertz. Okay, HZ is the number of, in that case, the number of radio waves that would occur per second. All right, another term. Another one that's new to us in the context of circular motion. It's related to frequency, closely related to frequency, but it's not the same thing. This time we're going to talk about period, which is abbreviated or which is given by the symbol capital T. Don't make it a lowercase t. Lowercase t represents, I don't know, the time that it took a car to travel 20 meters. Lowercase t might represent the time that it took a ball to fall 47 meters. Lowercase t might represent the time that it took the rocket to fly through the air. Lowercase t represents any amount of time, right? Capital T is specific period. Period is not the number of cycles per unit time, but rather it's the time for one cycle. So if you had, let's say you had, let's say you're married and you have an anniversary. So you have two big events per year, not just your birthday, but you have an anniversary. Okay, the frequency of a big event would be 2 times per year. Make sense? Okay, so frequency, not in hertz, but in cycles per year, it would be 2, right? The period of that, the period of one event, the time for one cycle would be 0.5. So it's the inverse of the frequency. If 2 of the events take place in a year, then it's half a year for one event between events. Make sense? 0.5 years in between events. It's the exact opposite of frequency. It's not the number of cycles per time, it's the time per cycle. Now, period would be given by a similar equation as frequency. As opposed to number of cycles per time, though, it would be the time over the number of cycles. Now, in the example that I just gave you, which was based on the example that Sonia gave us a few minutes ago, the period of that would be 0.5 years, right? Every 0.5 years, a new event takes place. Time is 1 year. The number of cycles was two events, okay, 0.5 years. But the standard unit for period is not years or days or weeks or hours or months or decades. The standard unit for period is going to be, what do you think it's going to be, Fraser? Seconds, right? Now, I saw a few minutes ago one person flipping back and checking her data sheet. And I think what was happening is she was probably looking for these equations on her data sheet. But she wouldn't have found them because they're not there. The reason these equations aren't there is because really they're not equations, really they're definitions. You have to know what frequency and what period is, and from the definitions, right, from this, you can pretty easily calculate the values. Now there is one equation on your data sheet that relates to frequency and period, but it doesn't look like either of the ones that appear there. Rather, looks like this. If frequency is cycles per time and period is time per cycle, then the period must be inversely related to frequency. In other words, the period is equal to the reciprocal of the frequency. Or similarly, you could say the frequency is equal to the reciprocal of the period. This is the one that appears on our data sheet. You're going to use that, but you're also going to use these ones, the ones that don't appear on our data sheet, the ones that come from the definitions that we just came up with over the last few minutes here. Finally, one more thing that this is not new to us at all, but the context in which we use it will be. We're talking about speed here now. We know what speed is, right? How fast something's moving. Well, if we're talking about speed in the context of uniform circular motion, my keys going around my head at a constant speed, or a car going around a turn at a constant speed, or a roller coaster going around a turn at a constant speed, then we're going to use the equation v is equal to delta d over delta t to describe that speed. Right? Speed isn't changing. If it's uniform circular motion, the speed must be constant. And if it's a constant speed, then we're going to describe it by v equals d over t. Now, listen carefully. My son's in grade 7, and my son has learned this earlier in the year in math class, so I know you guys know this, but it's been 4 years since you've learned it. The distance around a circle one time is called what? The distance around a circle one time is called what, Diamond? The circumference. You guys know what the circumference is equal to? I mean, we know what it means, right? It's distance around a circle once, but do we know what the equation is that represents the circumference? Rosie? Good. 2 pi r, or you could say pi times d. I like to use 2 pi r. I'm not sure why, but I do. 2 times pi times, what does r stand for? David? The radius of the circle. Good. Now, if we're going to say the speed of the object, the speed of these keys going around in uniform circular motion around my head is equal to 2 pi r over something. In other words, the distance around the circle once, then what are we going to put on the bottom? On the top, we're saying the distance around the circle one time, the circumference. What goes on the bottom? What goes on the bottom there? Ben, do you think you know that? The time around the circle once, right? The distance around the circle once, the time around the circle once. Ben, what is the time around the circle once? Sure you do. Stare you right in the face, literally. The time that it takes to go around the circle one time. The time that it takes for one cycle. 1 over f, or you could say t, the period, right? So let's just say 2 pi r over t. This one also appears on our data sheet. V equals d over t absolutely applies here, distance over time, but in the context of uniform circular motion, it's going to become circumference divided by the period, 2 pi r over t. What do you think the units are going to be? 2 times pi times meters over seconds. Of course, it's going to be meters per second, just like it always has been, meters per second. Okay, I want to take a look at an example on page 250. This is chapter 5, by the way, if you don't have that downloaded already. This is the hard drive of a computer stores data on a thin magnetic platter that spins at high speeds. The platter makes one complete revolution in 0.00833 seconds. Picture that. Okay, you got this little platter inside a hard drive. You don't see that. If you take the hard drive out of a computer or maybe an external hard drive, you don't actually see what's going on. But basically it amounts to like a CD spinning around, except it spins around really, really fast. It makes an entire rotation in 0.00833 seconds. So in other words, 8/1000ths of a second. That's how long it takes this magnetic platter that stores the information in your hard drive to make one complete rotation. Okay, that's pretty quick. We want to find its frequency in hertz and in RPM. What does that mean? Yeah, rotations or revolutions per minute. In other words, that's not the standard unit for frequency, but it is one that we end up seeing fairly often, the number of cycles per minute that takes place. All right, we're looking for frequency. Clearly, we're looking for frequency. What do we have given to us here? 0.00833 seconds. Is that speed? Is that time? Is that distance? What is that? Looks easy, right? 0.00833 seconds. It's a time, right? But we got to be specific here. It's not just any time. It's not little t. Specifically, it is. William, what's the value that we have here? What variable is that? 0.00833 seconds. But what time is it? Specifically, what time is it? Good. It's the time for one complete cycle, or it's the period. So we're going to say big T is 0.00833 seconds. Do not call it little t. That's not going to be helpful to you. Okay, you want to call it big T so that you remember that it is specifically the time for one complete cycle. Now, how are we going to find frequency from this? This should be really easy at this point. F is equal to 1 over T. 1 over 0.00833 seconds. Let me show you a little trick on your calculator to do that. And obviously, on your calculator, you can say 1 divided by blah, blah, blah. Or here's another little trick. You can say 0.00833 x to the minus 1. That says 1 over whatever number you have there. So it saves you a couple of keystrokes of entering it. Whenever you want to go 1 over something, just hit the number and hit x to the minus 1 in the calculator. We end up getting 120.048. What are the units here? Well, it would be cycles per second, or don't hurt me here, right? Don't hurt me. You know this. Okay, what is it? Hertz. We're gonna turn that into 3 digits here because these zeros are not significant, but the 833 is. 3 significant digits there. Final answer is going to be 120 hertz. So think about this. This platter in the hard drive is spinning around at 120 rotations per second, 120 times per second. That's why you can access data so quickly on a hard drive, right? It's scattered, data is scattered all over the place on this hard drive, but because it's spinning so quickly, you can access it still fairly quickly. All right, we want to find its frequency in revolutions per minute now, or rotations per minute. If it's 120 rotations per second, or 120.048 rotations per second, we're going to divide by 60 to get the number of rotations per minute, because there's 60 seconds in a minute, right? Sorry, not divide by 60. What are we going to do? What are we going to do? Multiply by 60, right? And I think what we end up with there is 7,200, or 7.20 times 10 to the 3 RPMs. That's a pretty standard value, by the way, for the frequency of a hard drive is 7,200 RPMs. You can get hard drives that spin faster. What would be the advantage of having a hard drive that was, say, 9,600 RPMs versus 7,200 RPMs? Who cares? It has nothing to do with capacity. Right? The hard drive, the capacity of the hard drive isn't based on how fast it spins. What's the advantage of, say, 9,600 or 12,000 over 7,200? We get to our data faster, right? The faster it spins, the quicker we get to access the data that we have stored on there, because the quicker it gets to the point where it pulls the data off, right? Have a look at those 3 questions, please, on page 250. All right, here's another example, 5.2. It says a pebble is stuck in the treads of a tire at a distance of 36 centimeters from the axle. Hey, why did I circle that? Why did I circle particularly in red? Miles? It's in centimeters. I'm going to want to convert that. And I just wanted to remind myself that I got a conversion to do here, right? 36 centimeters from the axle, it takes just 0.40 seconds for the wheel to make 1 revolution. What's the speed of the pebble at any instant? What do we have here? Let's draw it out here. They give us a diagram in the book, but I don't think you need that. I think you can draw your own diagram here. Here's the treads out here, right? The treads of the wheel. And here's the axle in the middle. And this 36 centimeters is the distance from this stone that's stuck in the tread to the axle. What variable is that? Is that a displacement? Is that a velocity? What variable is that? Robbie, what variable would that be? 36 centimeters. That would be the radius, right? That would be the radius of the circle. We got another one here as well. It's 0.40 seconds. What variable is that? Is that t, little t? Emma, what's that going to be? That's going to be big T. Good. The time for one revolution. Don't call it little t. That's just any time. Okay, this is specifically the time for one complete revolution. This is a special time. Give it the respect it deserves by making it a capital T, not some piddly little lowercase t. All right, we want to find the speed. And we know the speed of an object going in a circle is 2 pi r over the period. Now, we have the period. If we didn't, then maybe we could find the period by saying 1 over f, right? That happens sometimes. If we're given the frequency instead. We know the radius here. We've got to convert it to meters. 0.360 meters. Divided by the period of 0.40 seconds. Let's pull the calculator out again for that one. 2 times pi times 0.36 divided by 0.4. Gives me a speed of 5.65 meters per second. I used to have a little bike computer, it's called, but really what it was is just a little speedometer / odometer on my bike. Anybody have one of those? Like a little thing that goes on the handlebar, tells you how fast you're going, tells you how far you've gone. They're almost obsolete now because now you can do everything by GPS, right? With your phone or whatever, determine how fast you're going or how far you've gone. But they still sell them though. And the way that worked was that we would put, you get this little computer, you'd put it on your handlebars, and you'd have to put this little magnet on a spoke somewhere. So let's say these are the spokes of your bike. Probably have more than 4, but simplify it a little bit. You put that little magnet somewhere on a spoke. It doesn't matter where on the spoke it goes. It doesn't matter whether it's close to the treads of the tires or close to the middle. It doesn't really matter. What happens is that as your wheel turns around, that magnet gets detected. There's a little sensor on the fork of the front fork of your bike that senses every time it goes around, and it times it. That's all it does. That's all your bike computer detects is the time, how long it takes for that little magnet to go around once. That's all it does. And then a little computer inside this little speedometer thing calculates speed and distance and so on. It calculates speed by this equation. Now, t is the time that it would take for this little red magnet to go around once. Doesn't matter where it is though. So how does it calculate speed correctly if r can be whatever? R would be not the distance from there, r would be the distance to the outside, the radius of your wheel. So basically, if this goes around one time, then that means your wheel has gone around one time as well. And we know the radius of your wheel, so we could calculate the speed of your bike, or the computer could calculate the speed of your bike by saying 2 times the radius, times pi times the radius of your tire, divided by how long it takes your wheel to go around one time. And it repeats that calculation every single time your wheel goes around. And then from that, it can calculate distance and so on. Make sense? All right, take a look at these 2 questions, please. I want to take a quick look at question number 2 here, and then we'll move on just a little bit further here today, all right? This one says, in 2006, an Alberta astronomer discovered the fastest spinning pulsar ever found. It has a radius of 16.1 kilometers. So think about this. We're talking about a star, a collapsed star, but a star that has a radius of 16.1 kilometers. Okay, that's the distance roughly from here to Shaughnessy in Calgary. That's the size of this star, is the distance from here to Shaughnessy in Calgary. 16.1 kilometers, which of course we're going to want to convert to meters. It's spinning at a rate of 716 hertz. That's a frequency at which it spins. 716 times around per second. So we're talking about the fastest spinning pulsar ever discovered. That's pretty fast, 716 cycles per second. We want to find its speed. In other words, how fast this thing is moving at the equator. Now, depending upon whether it's a perfect circle or not, it may be moving at different speeds in different places. Its frequency would be the same no matter whether we're talking about the equator or somewhere else, but its speed wouldn't necessarily be the same because the radius somewhere else might be a little bit different. All right, so what are we going to do? We're going to say R is 16.1 kilometers. We're going to convert that to meters. We get 16,100 meters. Our frequency is 716 hertz, and we want to find the speed. We know to find the speed in the context of circular motion, we're going to say 2 pi r over t. We know what r is. 2 times pi times 16,100 divided by a period. Do we know what period is? No, we don't. So how are we going to find that? Julia, how are we going to find the period there? Good. 1 over the frequency. So we're going to say 1 over 716 hertz. Who's down? Do you got a value for that? 1 over 716? I thought I saw your hand going up there. No? Julia, you have that? 6. Okay. So we're going to, that's a pretty small period, right? 1/1000th of a second that it takes this thing to spin around. Let's plug that in here. 0.001396648 seconds. We end up getting 7.24 times 10 to the 7 meters per second. That's pretty fast. Okay, that's pretty fast. Like we're talking about a speed that's approaching the speed of light here, which is the fastest possible speed for anything. Okay. First of all, you don't want to be anywhere close to this pulsar. But if you were close to this pulsar and you were on the equator of this pulsar, the good news is it's spinning around so fast that you'd be, again, you don't want to be anywhere close to this thing. You'd be spun away from this. You'd end up flying off into space so quickly because it's spinning so fast. It's like if the Earth was spinning so much faster, what would happen to us? We'd fly off into space, right? We don't because gravity is strong enough to keep us in. But if we're spinning that fast, we would. All right, last little bit here, and then we'll wrap it up for the day. I told you a little while ago, half an hour ago, I said, look, we're studying circular motion and gravitation, and specifically in the circular motion part, we're talking about uniform circular motion. Circular motion in which the object is moving at a constant speed. If it isn't speeding up and slowing down, if it's going at a constant speed, how is it that we can talk about something like acceleration or force? Well, here's the deal. When we're talking about uniform circular motion, the speed isn't changing, but the velocity is. The velocity is changing because the direction changes. And remember, speed is how fast something's going. Velocity is the rate of change of position. It's a vector. So you can be going at a constant speed, but yet changing direction. The speed is constant, but the velocity isn't. The velocity is changing because of the direction changing. Acceleration is not how quickly the speed is changing. Acceleration is how quickly the velocity changes. So if you change direction, it doesn't matter if you go at a constant speed. If you change direction, your velocity changes, and therefore you experience an acceleration. So as I swing those keys around my head again, in the example that I've given you a few times so far, as I swing these around my head, the keys are moving at a constant speed. But yet, as they do that, they accelerate. They don't speed up or slow down, but they accelerate because the velocity is changing. The direction is changing. So there is, in all the problems that we've done so far, there is an acceleration. It's just not the acceleration that we typically think of when we talk about acceleration. That acceleration we're going to call a centripetal acceleration. It's the acceleration of an object moving in a circle And that acceleration is directed toward the center of the circle. That's weird. Okay, that's weird. The acceleration, centripetal acceleration, the acceleration that an object in uniform circular motion experiences is always directed toward the center. It's always directed toward my hand that's spinning these keys around. Or if you got a car racing around a track, it's always directed toward the center of the racetrack. Or if you got a roller coaster going around a loop, it's always directed toward the middle of that loop. Or if you've got a hard drive spinning around, it's always directed toward the middle of the hard drive. Or, wait a second, a car going around a turn with 5 people in the back seat being thrown to the outside, the acceleration is always toward the middle of the circle, not towards the outside, but toward the middle of the circle. I'll explain why you get thrown to the outside if the acceleration is toward the middle of the circle a little bit later on. So it's the acceleration of an object moving in a circle directed toward the center of the circle. If there's an acceleration, there's got to be a force. This is the force that causes the acceleration toward the center of the circle. In other words, it's acting toward the center of the circle as well. This is actually an easier one to understand, I think. One more time. As I spin these keys around my head, they want to go in a straight line, right? Newton's first law says they will go in a straight line forever until acted upon by an unbalanced force. So if they're not going in a straight line, something must be keeping them from going in a straight line. A force, right? There has to be a net force that causes them to not go in a straight line. What's causing that force? Look at this. Literally, look at what I'm doing right now. What is causing the force on these keys? What's causing, Natalie, the force on these keys? What's pulling on these keys? My hand. My hand is supplying the centripetal force there. Where is my hand relative to this circle? In the middle, in the center. So if my hand in the middle of the circle is pulling on the keys, then the force must be toward the center of the circle. That force that acts toward the center of the circle we call the centripetal force. Now you can see maybe why the acceleration is also toward the center. If the force is toward the center and F equals ma, then the acceleration's got to be toward the center of the circle as well. Centripetal means center seeking. So if you have a centripetal acceleration, it's a center-seeking acceleration, an acceleration toward the center of the circle. A centripetal force, a force toward the center of the circle. We're going to give you an equation for the centripetal acceleration. Notice I put 2 absolute value signs around it, meaning that centripetal acceleration is a vector, and the acceleration is, but this equation is not going to tell me the direction. That's okay. We don't need to be told the direction. We already know which way it's pointing. The centripetal acceleration is already, we already know it's pointing toward the center of the circle. It's going to be v squared over r, the speed squared divided by the radius of the circle. And the units, of course, are going to be meters per second squared. The centripetal force, it's m times a, or it's m times v squared over r. And the units for centripetal force toward the center of the circle are newtons. Both of these equations are on your data sheet. One more little thing here. Even though an object is moving in a circle, the acceleration is toward the center of the circle, and the force is toward the center of the circle. if this object is moving around in a circle like this, counterclockwise, then the velocity is always a tangent to the circle. It's kind of a line that skips along the circle. I remember what Newton's first law says. An object in motion will stay in motion in a straight line until acted upon by an unbalanced force. This object wants to keep going out like this, and it will keep going out like this unless a centripetal force pulls it inward, takes it out of its straight line path. I was to swing my keys around one last time today. I was to let go of them. I was to take away the centripetal force. They wouldn't go outwards. They would just go off in a straight line at a tangent to the circle, like those keys did. Or sorry, like that object in that diagram does. All right, let's just do one question and then we'll wrap it up for the day here. It says a DVD. I mean, when this book was written, DVDs were, that's the way people watch movies. And then we went to Blu-rays, which is for a while the way people watch movies, and now everybody downloads their movies now, right? People still buy Blu-rays, I guess. Not so much DVDs, though. Anyways, a DVD and a Blu-ray, by the way, they're the same size. It's just how the information is stored is a bit different here. A DVD has a diameter of 12 centimeters and a rotational period of 0.1 seconds. What's the acceleration of the outer edge of the disc? So not how fast is it moving, but what's the acceleration of a point on the outer edge of the disc? We have a diameter of 12 centimeters. We're going to make the radius 6 centimeters. We don't want diameter because the equation we have is 2 pi r over t for speed. So we want radius. The period here is 0.100 seconds. Looks like all we have. We want to find the centripetal acceleration. We know acceleration is v squared over r. We don't know what v is. So we're going to say v is equal to 2 pi r over t. 2 times pi times 0.060 meters divided by the period of 0.1 seconds. Let's figure out what that is. 2 times pi times 0.06 divided by 0.1 gives me 3.7699 meters per second. That's way slower than the speed of a hard drive, right? It was way slower than a hard drive was spinning. 3.7699 squared divided by r, 0.060 meters. Gives me an acceleration of 236.9 or 237 meters per second squared. On your field trip to West Edmonton Mall, you're going to have a number of problems where you have to find the acceleration of something. The acceleration of a roller coaster cart as it goes around a turn. The acceleration of you as you accelerate upwards in a ride. If you were to find the acceleration to be 237 meters per second squared, first of all, that would be a really, really high acceleration. A lot of those questions end up being followed up by another question that says, how many G's is this? The G force that you experience. Okay. I know I'm going to get this question a million times as you're going through your assignment. How do you calculate G's? Well, all I would do is say, let's take the acceleration, 237 meters per second squared, divide it by 9.81. And that's going to be somewhere in the range of 24. 24 G's. In other words, if you were standing on the outside of a DVD as it spun around at that speed, you would feel 24 times heavier than you really are. Okay? That would be your apparent weight, how heavy you feel compared to how heavy you really are. Okay? That's what G's mean. It's simply acceleration divided by the acceleration due to gravity. All right, I'd like you to do these 3 questions, and we're done for the day.